Alright, today we're doing a React video. We're going to be learning more about PID controllers. Apparently they're in everything, like from robots to toasters, so I thought it'd be good to learn about them finally. We're going to be watching this video called PID Controllers Explained by Real Pars, so let's get into it.
In this video, we're going to talk about the PID controller and its transformation from a single station device to what it has evolved into today. We're going to explain why PID controllers are used in industrial processes instead of simple on-off controllers.
Yeah, that's what I'm saying.
We'll illustrate how controller settings called proportional, integral, and derivative affect different processes under control. We'll also provide an overview of the very important activity called controller tuning. Let's start with a discussion about home temperature control, as it's familiar to lots of people. This house has a furnace that distributes heat throughout, and a wall-mounted controller called a thermostat. The thermostat has a sensor that measures the house temperature and compares that measurement to an adjustable set point. If the room temperature is below the set point, the furnace is turned on. When the room temperature increases above the set point, the furnace turns off.
This is a side note. I feel like sometimes thermostats don't work like that. I swear I put it on like 60, 68, 67, and it's still 75 degrees in the house. I don't get it.
This type of control is referred to as on-off or bang-bang control.
Bang-bang control. Okay, so let's write that down. You got that bang-bang, you know what I'm saying?
Here's a plot of what the room temperature does over a period of time as the furnace turns on and off. As you can see, the temperature is not exactly held at the set point of 70 degrees Fahrenheit, but cycles above and below the set point. On-off control may be okay for your house, but it is not okay for industrial processes or motion control. Let's look at an example of tank level control to explain why. The valve fills the tank as the pump drains it. If the valve is operated with on-off control, the water will fluctuate around the 50% set point.
Yeah, makes sense.
For our purpose, let's say the fluctuation is plus or minus 10%. In most industrial applications, this fluctuation around the set point is not acceptable. Okay, well, what if it's possible to throttle the valve and place it in any position between on and off? Now we can move on to talking about a PID controller.
Okay, I feel like
P stands for proportional, I stands for integral, and D stands for derivative.
Okay.
Because
I like where this is going. You know, I love math. Because I'm Asian. Sorry.
As every process responds differently, the PID controller determines how much and how quickly correction is applied by using varying amounts of proportional, integral, and derivative action.
Okay.
Each block contributes a unique signal that is added together to create the controller output signal.
Alright, so what I'm getting so far is that the PID is important for kind of like fine-tuning the error and like the differences. So it doesn't fluctuate as much. So that seems like the purpose of PID.
Let's look at how a PID controller fits into a feedback control loop. The controller is responsible for ensuring that the process remains as close to the desired value as possible, regardless of various disruptions.
That makes sense. Okay, so I've seen this diagram a couple times before while working on the robot. From what I understand, like the set point is where, like when the robot sends a command, okay, so it's going to send a command to a set point, it has a desired value of what it wants to reach. So it's going to go through this loop where it goes through the PID controller, and the PID controller adjusts whatever, I guess, element, right, your final control element you need. And I don't know that this process block means, but basically it's like it's going to adjust the control element and keep running through this loop until it gets closer and closer to the desired value that was sent in from, would it be the controller? I'm not too sure. We're figuring that out right now, but I kind of get what's going on here.
And the set point. Based on that comparison, the controller produces an output signal to operate the final control element. This PID controller output is capable of operating the final control element over its entire 100% range. Most modern PID controllers are part of a PLC or DCS and are created in the program control logic using block commands. Before PLCs came along, a PID controller was a standalone device, responsible for controlling one loop. A control room would have dozens or hundreds of standalone controllers mounted on a panel. There are still many standalone PID controllers being manufactured and used today. Okay, let's get back and talk about what each of the P, I, and D components of the PID controller does. Remember earlier we said that the PID controller is responsible for ensuring that the process remains as close to the set point as possible, regardless of various disruptions.
Okay, so I'm understanding more. Set point isn't a desired value to reach and then it's done. It's actually just like the set point from the graph is the point at which we want to be at, right? That we don't want to fluctuate too much. We want to stay at that level as much as we can. Learning.
Let's refer to the difference between the process variable and the set point as the error signal. The proportional block creates an output signal proportional to the magnitude of the error signal. Unfortunately, the closer you get to the set point, the less it pushes. Eventually, the process just runs continuously close to the set point, but not quite there. That's when integral jumps in. The integral block creates an output proportional to the duration and magnitude of the error signal. The longer the error and the greater the amount, the larger the integral output. As long as an error exists, integral action will continue. The derivative block creates an output signal proportional to the rate of change of the error signal. The faster the error changes, the larger the derivative output. Derivative control looks ahead to see what the error will be in the future and contributes to the controller output accordingly. That brings us to a term called controller tuning. We said earlier that every process responds differently.
I'm gonna have to watch that again. Oh, mercy. That was a little bit much. Let's try again. So,
let's refer.
Wait, okay. What am I not getting? I think it's like, all right, I understand there's a set point, and that the error is the difference between the set point and the process variable, or like what's the output. I understand that, but okay, like I feel like what I understand right now is that the proportional, integral, and derivative parts, they all like modify the magnitude of what is this?
PID controllers respond
or the process variable based on the error, and I'm just trying to figure out how that all relates. So I'm going to watch it.
Responsible for ensuring that the process remains as close to the set point as possible, regardless of various disruptions. Let's refer to the difference between the process variable and the set point as the error signal.
Okay.
The proportional block creates an output signal proportional to the magnitude of the error signal.
Okay, so the proportional block creates a signal. I'm literally going to say this 3 times. The proportional block takes the error and it's proportional to the error. So it might not be the same value, but it should follow the same, what is it called? The same pattern, word. Anyway, you understand what I'm saying.
Unfortunately, the closer you get to the set point, the less it pushes.
Okay, so the problem is though, because it's proportional, once the error is 0, the set point is not going to be 0. From what I understand, because from the calculations, it's like it might have the same shape, but it might not be at the same level where the set point is.
Eventually, the process just runs continuously close to the set point, but not quite there. That's when integral jumps in.
Come on, say
the
this,
integral block creates an output proportional to the duration and magnitude of the error signal.
Okay, so this is the second part. So the integral part is like, okay, it's called integral because error is the slope of the integral action. So the longer there's error, the integral action will go up.
The longer the error and the greater the amount, the larger the integral output.
Okay.
As long as an error exists, integral action will continue. The derivative block creates an output.
Okay, that makes sense. As long as an error exists, so if there's any deviation from the set point line, that creates a slope for the integral portion, which is going to add values to the graph, if that makes sense. So if we're below the set point value, then the slope is going to be down, and if it's above, it's going to go up.
Integral action will continue. The derivative block creates an output signal proportional to the rate of change of the error signal.
I can cook with that. I can cook with that. Okay, yeah. This is just calculus, guys. That's fine. favorite
After
subject.
the error changes, the
Gotta
larger
stop
the
doing that.
derivative
I'm really
output.
gonna stop. Okay, we're locked in.
Derivative control looks ahead to see what the error will be in the future and contributes to the controller output accordingly. That brings us to a term called controller tuning.
Okay, controller tuning. So from what I understand, it seems like all three of these properties, proportional, integral, and devotional, derivational, holy freak, dude, I'm illiterate, contributes to controller tuning, or kind of like fine tunes all those things. I think we're gonna see that right now.
That every process responds differently, and that the PID controller determines how much and how quickly correction is applied by adjusting proportional, integral, and derivative action.
Oh,
Controller
okay. So each individual part, it's not like they're all equal and they get thrown together. It's like each part has a different amount that they can adjust for like the error.
Tuning involves correctly setting the controller P, I, and D values for specific process requirements. Interestingly, the correct settings achieved by controller tuning can differ vastly between processes because of specific requirements.
That makes sense, right? Not everything's
For example,
one size fits all.
after the controller has been tuned, a set point bump of 1% in a tank level control produces a quarter wave damped response.
Of course,
This
the
type of
quarter wave
response
damped
may be
response.
suitable in a tank level process, but could be disastrous in a motion control process. There are many different manual methods for tuning a controller that involves observing the process response after inflicting controller set point process. There are many different manual methods for tuning a controller that involves observing the process response after inflicting controller set point changes.
Okay, so it's not like automatic. Like you gotta like play around with the settings and see what fits, you know?
One method involves increasing the amount of set point change and repeating the procedure until the process enters a state of steady state oscillation.
Oh, that
This
not
method of tuning produces adequate results, but is often impractical in many applications.
Let's say it looks
For
a little bit-
example, how practical is it to force the fluid level in a large tank to reach a steady state oscillation? Most process controllers, PLC, and DCS loop controllers sold today have auto-tuning capability.
Auto-tune? Oh wait, say less. Yeah, you know where that's from.
PID controller learns how the process responds to a change in set point and suggested PID settings, regardless of whether the initial PID parameters are derived from the manual or auto-tuning methods. Additional tweaking is often required by seasoned automation professionals to get the response desired.
Yeah, that's your seasoned guy right there. Look at him. Look at his face. He's been through so much. He's like Saitama, bro. He's just lost all feeling because of how fetching cracked he is at controller tuning.
That should do it for this video.
Look at the guy.
If you want to learn more about
it's
PID
over?
control, let's review.
Okay, wait, there's a review
An
section.
on-off or bang-bang controller has only two output
How do I find it so bang bang controller?
conditions and switches abrupt
Alright, let's restart.
description.
We gotta restart. We gotta
Bang-bang
restart.
controller has only two output conditions and switches abruptly between these two conditions.
Okay, so this was the original thing, right? The problem to be solved was that there's in the on-off control, there was only on and off, so it had this fluctuating problem that was not good for some systems.
In a PID controller, P stands for proportional, I stands for integral, and D stands for derivative. The PID controller is responsible for ensuring that the process remains as close to the desired value as possible, regardless of various disruptions. The PID controller determines how much and how quickly correction is applied by using varying amounts of P, I, and D action.
Which we talked about.
The proportional block creates an output signal proportional to the magnitude of the error signal.
Oh, we're gonna go through this again. Yeah, okay.
The integral block creates an output proportional to the duration and magnitude of the error signal.
So it's just the integral
The
of the error,
derivative
and
block
then
creates an
derivative of the
output signal proportional to the rate of change of the error signal. Controller tuning involves correctly setting the controller P, I, and D values for specific process requirements, either manually or automatically.
Automatic. So sick.
Want to learn PLC programming in an
Alright, I think that's it.
easy-to-understand
All right, that's pretty simple. I don't think I got into like the quantum realm of PID controllers, but It was definitely good information to know, and I think I'll definitely use it for the robot because it's a, what is it called? It's in a manipulator, so definitely you don't want fluctuations. I guess I don't really know how to apply it yet. We're gonna learn about that, but they said it. So anyway, catch you on the flip side.